Okay, so this video is going to cover factoring. One of our special types of factoring techniques that we have is the difference of squares. So one of the first things that we would need to know in order to do a difference of squares problem is, first off, do we know if we have difference of squares? And there's a couple of stipulations that come with that. Now, there's three things that we need to look for in order for us to know for sure that this is difference of squares. The first is that we have two terms. That tends to be the most obvious one. When looking at a factoring problem, we tend to have 2, 3, or 4 terms. So when we have 2, that almost always means difference of squares. But every once in a while it doesn't, so we do need to check the second and third stipulation. Now the second one is that we have different signs. One of our terms has to be positive, the other term must be negative. And looking at this problem that we do have here, we do see that the x squared is a positive term, and this 121 over here, we have that minus sign in front of it, so that works. Third stipulation says that both terms must be perfect squares. So then, what is a perfect square? So a perfect square is a factor that can be multiplied, or a number that has a factor that can be multiplied to itself to get that. For example, the number 25 would be a perfect square because 5 times 5 gives me 25. 36 would be another example of a perfect square because 6 times 6 is 36. A non-example would maybe be something like 24. 24 is not a perfect square. We do have 2 times 12. We do have 6 times 4. We still have factors that multiply to get it, but the factors must be the same. 2 and 12 or 6 and 4 are not the same factor. Whereas over here with 25, the 5 times the 5 is the same thing. 6 times the 6 is the same thing. So then taking a look at the example that we have here, are these terms perfect squares? Well, then we need to think, okay, what times itself will give us x squared? And the only possible way to get x squared here would be to get an x times an x. And hey, those are the same factor, x times an x. That would work. And then we need to look at 121, and we need to think, okay, what number times itself would give us 121? Well, 121 just happens to be 11 times 11. So these are perfect squares, which means this problem does fit all three stipulations. So then as long as we do have difference of squares, our formula says this. It says that our polynomial will factor to a plus b times a minus b. So a and b are just those perfect squares. So taking a look at x squared, right? Our a would be what times what gives me the first terms. Well, we already said that x times x would give us that x squared. So a is x for this problem. B would be what times what gives me my second term. And 11 times 11 gives us 121. So here's my a and b. So in order to factor this problem, it'd be my a plus my b, and then my a minus b. So here I have x plus 11 times x minus 11. This would be the solution to our problem. Also remember, when it comes to factoring, if we want to check our work, we can always backtrack and multiply our terms together so we can distribute here and double check that we are getting our original problem. Okay, so let's try another example. All right, so here we have another example, so let's go through our criteria for it being different squares. We do see that we do have two terms here, right? We have 1, 2. Then we need to check, are they different signs? So the 9x squared is positive, the 64y squared is negative, so that's good. We have different signs. Third check, are they both perfect squares? Well, let's see. Let's see if we can try and figure out what is our a, what is our b. So a, right, what times what would give me a 9x squared? So in this example, our term, we have a number and we have a variable for this example here, we have a number and our variable in this first term here. So then we need to kind of almost split this up and think what times what gives me the 9, what times what gives me the x squared. Well, I know that 3 times 3 gives me a 9. I also know that an x times x gives me x squared. So it would make sense then that 3x times 3x is 9x squared. Moving over to b, I need to think what times what is going to give me the 64 and what times what is going to give me y squared. Well, 8 times 8 happens to be 64, and y times y happens to be y squared. So difference of squares is going to factor to your a plus your b, and then your a minus your b every time. So that would look like 3x plus 8y times 3x minus 8y. And that would be the solution to our problem here. Also remember, you can always multiply to double check. All right, so looking at another example, again, we are factoring here. So here we are working on difference of squares, but let's run through the criteria anyways. So the first one says that we have 2 terms. So here we have 2 terms. Second criteria says that we must have different signs. So looking at the 16x squared, it's positive. Looking at the 81, it's also positive. So these terms have the same sign. They don't have different signs, which means they don't meet that second stipulation, which means this is not difference of squares. So we cannot factor this using difference of squares. We are going to call this prime, which means it's unfactorable. We could then check to see if we maybe have a greatest common factor or any other thing that we can do here, but we don't have a greatest common factor with the 16 and the 81, so that would not work here. So we do state that this problem is prime. Okay, so the last example here that we're going to have is this one here. So let's go through our criteria one more time. First criteria is that we have 2 terms, so we can easily see here we have 2 terms. Second criteria says we must have different signs, so taking a look at x to the 4th, that is positive. Taking a look at 81, that is negative because of that minus sign I have there, so they do have different signs. Third criteria, they must be perfect squares. So let's see, do we have an a and a b that would work here? Okay, so then taking a look at our first term, what times what gives us an x to the 4th? So if we have to multiply to get x to the 4th, we need to remember the product rule. And remember that the product rule says that when we're multiplying like bases, which we would have to have here, that we would add those exponents. So what number plus the same number gives me 4? Well, 2 plus 2 is 4. So that would then follow that x squared times x squared is x to the 4th. Again, using the product rule, if we did x squared times x squared, product rule says keep the base, add those exponents, 2 plus 2 to give me the 4th. So x squared times x squared is x to the 4th. So then moving over to b, what times what gives us 81? Well, 9 times 9 happens to be 81. So that when we factor this, this would factor to x squared plus 9, and then x squared minus 9. But I want you to pause and take a look at our answers that we have here. Take a look at these factors, x squared plus 9, x squared minus 9. And maybe pause for just a couple of seconds and see, do you notice anything in particular about this? Now, I can tell you right now that these 2 factors that we have here, this is not our final answer. And the reason why it's not our final answer because of the second term that we have here. And take a look at that second. The second factor happens to have 2 terms inside of it, an x squared and a 9. They are different signs because x squared is positive, the 9 is negative. And hey, these happen to be perfect squares because, well, x times x is x squared, and 3 times 3 is 9. So one of our factors happened to be a factor that could be further factored using the difference of squares again. So essentially we have difference of squares inside difference of squares. Now this first term, this x squared plus 9, is not difference of squares because it doesn't fit the second criteria that says they have to have different signs. Both of these terms are positive. So this term I'm just going to drop down, x squared plus 9. Now, the second factor over here, we're going to factor it one more time using the a and the b that we stipulated here. So that would give us x plus 3 times x minus 3. This would be our final answer here for this.